Robotic foundation models, based on pre-trained vision language models, or VLMs, have displayed a promising ability to solve complex open-world robotic tasks by combining common-sense reasoning with end-to-end control. However, robot foundation model-based approaches are usually single-shot. That means if they fail, we don't have a mechanism to learn from that failure in order to try again. In this work, we present learning from inference-time execution, or LITEN, which progressively learns to solve complex tasks with robot foundation models by attempting a task, learning from that experience, then using those learnings in order to improve future attempts until we are able to solve the task. Let's take a look at an example to understand how LITEN works. Here, a robot arm is asked to empty two of the bowls on the tabletop by moving objects between bowls. LITEN starts by employing an off-the-shelf VLM to generate a plan of subtasks for a Vision Language Action Model, or VLA. In this example, the VLM first suggests moving the orange fruit to the gray bowl, and then moving the curved blue block to the gray bowl in order to empty the pink and red bowls. As we can see, we failed our task of emptying two bowls. In order to understand why, and to generate useful feedback for future attempts, LITEN will take this failure and give it to a VLM along with a novel prompting mechanism. Through LITEN's prompting mechanism, the VLM is able to correctly identify that the red bowl was too small for the arm's gripper. The VLM also identified that the VLA had trouble reaching into the pink bowl to grasp the blue block. LITEN takes these conclusions generated by our VLM judge and adds it back in context for a future attempt at the task. In a subsequent attempt, LITEN generates a plan that instead suggests moving the tall yellow and red blocks from the shallow black bowl and the grapes from the large gray bowl, and is able to accomplish the task successfully. We present a diagram of the LITEN method here. LITEN uses a VLM to generate a step-by-step plan for a VLA, execute that plan, then accumulate meaningful takeaways from that execution by processing it with the VLM judge. We show LITEN's efficacy in two other complex tasks by showing an initial failed attempt followed by a successful one. Here, the robot is tasked with stacking three objects atop one another. Through experience, LITEN learns which objects can be more easily stacked based on physics and the VLA's biases towards certain objects. In another task, LITEN moves objects off the table by learning which objects the VLA-controlled robot can grasp, and then which objects can balance on top of others without falling or rolling off. Our main results show that LITEN strongly outperforms existing baselines for iterative self-improvement.